Let's now look at an example of how we can transform a time domain function to the frequency domain using the Laplace transform. So we want to find the Laplace transform of this function f of t, which is equal to delta of t plus 2u of t minus 3e to the minus 2t times u of t. Okay, so that's a little more complicated than what we've been looking at because we notice we have several parts. Well, let's sort of start with what we know. So from our table of common pairs, we know the following. We know how to take the Laplace transform of our delta function. So our Laplace transform of delta of t, we said, is just 1. We know that the Laplace transform of our step function just by itself is going to be 1 over s. And then we also know the Laplace transform for our decaying exponential, so that's e to the minus at. And so we found earlier that that was equal to 1 over s plus a. And so what you'll notice here, when I've written this expression, I've implicitly assumed that we have that step function multiplying by our decaying exponential. And so that's how you'll see it in the table. But up here we have this u of t, which is just defining this function for t greater than 0. So this is just defining for t greater than 0. And so of course, I mean that it's defining this decaying exponential for t greater than 0. Okay, so what we can do then is if we sort of know each of these parts, we can use our linearity properties. So let's do that. So our linearity properties, clean that up a little bit. So our linearity property had sort of two parts, and that dealt with when we were combining, when we were adding or subtracting multiple things, but also when we were multiplying by a constant. So we can say then in general that our f of s is equal to the Laplace transform of our first function, which was just delta, plus 2 times the Laplace transform of our second function, which was our step function u of t, and then minus 3 times the Laplace transform of our e to the minus 2t times u of t. And again, keep in mind this u of t here is just defining our decaying exponential for t greater than 0. So you can see I've just pulled out our constants 2 and negative 3 out front of the Laplace transform, and then as we're adding or subtracting in the time domain, we're adding or subtracting exactly the same in our frequency domain. So using our known properties that we wrote up here, what we can then say is that this overall Laplace transform f of s is equal to 1 for our Laplace transform of the delta, plus 2 divided by s for that step function term, minus 3 over s plus 2. Okay, so typically what we're going to want to do is we're going to want to combine all of these so that we just have one sort of fraction of variables. So the easiest way to do that is to find a common denominator. And so in this case, our common denominator, we can say is just going to be s times s plus 2. So we're going to have something in each of these divided by s times s plus 2. So I'm going to go ahead and write those out. So s times s plus 2. So of course, this 1, our first term, is going to have to be s times s plus 2 in the numerator as well, so that it's still 1. Our second term, we have to multiply that 2 by s plus 2, and technically by 1 as well, but that doesn't change anything, so that's going to become 2s plus 4. And then over here, we're just going to multiply by s, so we have minus 3s. And so what we can do then is we can, of course, just combine those terms into one fraction. So our common denominator, the s times s plus 2, and now we have s squared plus s plus 4. Okay. So now what we can do is we can ask ourselves, we found our Laplace transform, f of s, which we were looking for. So now let's ask ourselves, can we use our initial and final value theorems? So can we use our initial and final value theorems? And so our initial value theorem, we actually cannot use. So let's say this one is a no, and that's because of our delta function. So remember we said that our initial value theorem does not work if we have an impulse function, and in this case we see we do have an impulse function in f of t. So we cannot use our initial value theorem in this case. But we can use our final value theorem, so this should be good. And the only restriction on the final value theorem was we had to have a finite, we had to have a value for f of infinity, f of t equals infinity. And so we'll come back and talk about that later, but we do expect to have a final value there. And also we said in general for both of these theorems to work that our poles have to be in the left plane, the left half plane, but we could also have one pole at the origin. And so if we look at the poles of this function, we see we have one pole at -2 and one pole at 0. So we do have one at the origin, but that's allowed, so our final value theorem should be good. So let's see if we can't use our final value theorem. So remember our final value theorem, what we're interested in is we're interested in the limit as s goes to 0 of s times f of s. So if I just multiply through our f of s with s, what we have is s cubed plus s squared plus 4s in the numerator. And our denominator, I'm going to go ahead and factor through that s, so we have s squared plus 2s. And so, sorry, I need to have my limit over here on the right side as well. We just shift this over a little bit, and then let's come back in here and say this is the limit as s goes to 0. And so if we try to just plug in 0 for everywhere we have an s, we just get 0 over 0. So that's not very useful information. And so you might remember an old technique that we can use here, which is L'Hopital's rule. And basically what that's saying is we can take the derivative of the numerator and the derivative of the denominator and take the same limit. So we can say the limit as s goes to 0, and now taking the derivative of just looking at the numerator, we have that is 3s squared plus 2s plus 4, and taking the derivative just looking at the denominator, we have 2s plus 2. So now, as we take the limit, we see that all the terms with s's will go away, and we're left with just the 4 over 2, which is of course equal to 2. And so remember, what our final value theorem says is that this limit is equal to our f at t equals infinity. So, so the specific language, so let me just write sort of loosely, this is f of t infinity. The specific language we had was the limit as t goes to infinity of f of t, but basically it's the final value of our time function. So the question to ask ourselves then is, does this value make sense? So does this make sense? So in order to answer that question, what we want to do is we want to come back up here and look at our time domain expression. And so we see we have three components. We have this delta, which as we're going across in time, so if we sort of do a rough sketch here, as we're going across in time, our delta is just going to be sort of a blip on the radar. So we're going to have a sort of peak right here at 1, and that's all. Our 2u of t is going to kick on for t greater than 0, and that's going to be a value of 2. And it's going to look at like something like this. So we have this step function here, but then we also have this minus 3e to the negative 2t. And so basically what that's going to look like is we'll have some function down here which has some decaying exponential. And so let me draw it out a little bit. So we'll have something that looks like that. So of course what we can see is that this decaying exponential right here is eventually going to go to 0 as our t goes to infinity. Our delta, of course, is just happening right at our origin. So our final value then would just be the value of this step function. And because it has this 2 out front, we would expect that the limit as t goes to infinity of f of t to equal 2, which checks out with our final value theorem. And so again, keep in mind the reason we would do this is we can say with confidence that we have the correct f of s, and that way we can feel good about that before we spend all the time and effort to take the inverse Laplace transform and go back. Of course, in this case, we wouldn't necessarily do that because we just transformed this, but let's say we had done some analysis to get this f of s. Our final value theorem could be used to help verify the behavior before we spend the time and effort to inverse Laplace transform back to the time domain.